So, Samuel, we're moving from simple regression to image recognition. Pretty big leap, right?
Definitely. Image recognition's a huge field. It's where deep learning really shone.
Why is it so important?
Well, imagine identifying objects in pictures, recognizing faces, or even understanding scenes. That's image recognition. Cars use it for self-driving. Medical imaging relies on it. And more.
Gotcha. So, we're talking about a more complex dataset now?
Yeah, tiny images instead of just numbers. It's like going from counting apples to identifying apples in a basket full of fruit.
And how do we prepare this data?
We need to download it first. Then we pre-process it, maybe resizing or adjusting the image format. This gets it ready to feed into our network.
Okay, so it's not just about the network itself, it's also about the data.
Absolutely. The quality and quantity of the data greatly impact results. Bad data, poor results.
Makes sense. So, will the neural network be more complex?
Yeah, likely more layers and neurons to handle the nuances of images.
Great. This is exciting. So, what kind of networks will we be using though?
That's coming up. We're building up the foundation. Download, prep, then it's time to design.
So, Samuel, this Safar 10 dataset, pretty straightforward, right?
Yeah, it's a good starting point. Tiny images, a bunch of classes.
10 classes to be precise. What's the appeal? Why is it useful?
Well, it's simple enough to learn on, but still has enough complexity to teach us real-world stuff.
Like what?
Basic image recognition techniques. We can train models on it, see how they work. We learn how to classify.
So, it's kind of a training ground?
Exactly. It's a good baseline. People used to use it a lot. Now it's considered a bit outdated.
Outdated? Why is that?
More powerful datasets and models are available now. Things are more advanced. It's a stepping stone.
A stepping stone. So, it's not where the cutting-edge stuff happens?
No, it's not, but it's invaluable for understanding fundamental concepts. It's important to start simple.
Right. We want to understand the basics, but we also want to know what's next.
Absolutely. Safar 10 gets us to that point. It teaches us the components to build upon.
How many images are there in the dataset?
60,000. All these little pictures. So useful for a beginner.
32 by 32 pixels? That's tiny.
Indeed. It's a great way to get familiar with datasets and the techniques.
So we're looking at different objects, cars, birds, and so on.
Precisely. It's a very manageable learning resource.
So, what are some common issues people might encounter with Safar 10, if anything?
Sometimes, the simplicity can be misleading. You might overfit early on if the models are too complex.
All right, Samuel. So we're downloading Safar 10 data. Tell us about this dataset.
Yes, Safar 10 is a super common dataset for image recognition. Think of it like a mini library of images, used a lot in machine learning.
So, it's like a training ground for our models?
Exactly. It's got labeled images. That's key. We know what's in each picture.
And this code, what does it do?
It grabs the Safar 10 data. Crucially, it handles downloading if it's not already there.
So, why is that important?
Saves time. We don't have to hunt it down ourselves.
Right? And what are the options in that code?
Well, you tell it whether you want the training data or the validation set.
And what's the difference between those?
The training data is used to learn, while validation tells us how well the model is doing on unseen data.
Makes sense. So this Safar 10, it's like a standard benchmark?
Yup, lots of researchers use it. It's a common way to test image recognition models.
So, this is for training computer vision models?
Absolutely. They work with images and need this type of data to learn to recognize them.
You know, I'm picturing a bunch of pictures like cats and dogs, but way more complex.
Think everyday images, cars, trucks, birds, and so on.
Neat. And what's this about being a subclass of torch.utils.data? Dataset.
It means Safar 10 data fits into PyTorch's structure, a way to handle data efficiently during training.
So, it's designed for how PyTorch works?
Exactly. It makes it easy to use this dataset in PyTorch models. PyTorch knows how to deal with this type of data.
Got it. Makes it more streamlined. So this dataset object is not the data itself, right?
Exactly.
And how does that len method work?
Well, that tells us how many items are in the dataset. Like, how many books are in the library.
Makes sense. And what about get item
That's how you get a specific item, like a particular book. It gives you both the book, the sample, and information about it, the label.
So, it returns both the image and its label, an integer that describes it?
Yeah, like the category. Maybe 1 is automobile, 2 is truck, and so on. It's a super useful way to organize things.
So, this Safar 10 dataset, it's using PIL images?
Yep. Python Imaging Library. It's a standard way to handle images in Python. Very common.
And why is this structure useful in machine learning?
It separates the data from how you access it. It's crucial for efficient handling. Imagine if you had to load every image every time.
So, we can loop through the images one at a time, using this method?
That's right. We don't load everything in memory at once. Very important for large datasets.
Like how many images could this handle?
Well, the example shows 50,000. But with this approach, you can easily deal with much larger numbers.
Okay, Samuel, so we're talking about transforming images for use in deep learning. This tensor thing, what exactly does it do?
Well, Alfred, it takes an image, which is usually represented as a PIL image, and converts it into a PyTorch tensor.
A tensor? Can you unpack that for us?
Sure. A tensor is like a multi-dimensional array. Think of it as a table, but in multiple dimensions. Images, have height, width, and color channels.
Right. So, how does this tensor transformation work to represent these dimensions in the tensor?
It basically rearranges the data. Instead of having height, width, and channels as separate data structures, it puts the color channels first, then height, then width. So if you had a 32 by 32 RGB image, it'd become a 3 by 32 by 32 tensor.
I see. So, what's the crucial reason for doing this?
This format is standard in deep learning frameworks like PyTorch. Neural networks are designed to work best with this structured data.
So, it's kind of a translator for the network?
Exactly.
Why is that scaling important?
It prevents huge numbers from overwhelming the network. It's like normalizing the data, making it more manageable for the algorithms.
And using it with Safar 10 datasets, what's the advantage?
When you load the dataset with the transform, you get the image as a tensor instead of a PIL image. This means the network automatically understands its format.
So, it handles both image and label?
The label stays as an integer, but the image becomes a float 32 tensor.
That's really important to keep the image format consistent. And this conversion is needed before feeding data to a model?
Yes, absolutely. The model expects the input data to be in tensor format. No PIL format.
So if you don't use tensor, you might run into problems, correct?
Precisely. You might get errors or the network might not understand how to process the data.
Cool. So, we have to use permute to get the image back to a more visual format?
Yes, to show it in an image viewer, you need to rearrange the dimensions again. That's what the permute function does.
So a lot of effort involved, but crucial to a successful implementation. Got it. Thanks, Samuel. Okay, Samuel, we're talking about normalizing data. Why is this important in deep learning?
Well, Alfred, normalization helps deep learning models learn faster and more effectively.
Makes sense. So, how does normalization actually work?
We calculate the mean and standard deviation of each channel across your training data. Then we apply a transform.
You mentioned transforms. Can you elaborate on that?
Sure. These transforms are functions that modify the input data, like scaling or shifting values. A compose function combines multiple transforms. Think of it as a pipeline. This is super useful for combining multiple data augmentation techniques in one step.
So you're saying normalization happens in the data loading phase?
Exactly. It happens right as the data comes into the model, streamlining the process.
And you calculate these means and standard deviations offline?
Precisely. We compute them on the entire training set beforehand. then apply them to all subsequent data. That's a critical step for efficiency.
Got it. Now, that code you showed manipulates the data a bit.
Right. It stacks all the images to create a tensor that we can process efficiently.
The code then computes the mean and standard deviation for each channel. What does view 3 minus 1 mean?
That reshapes the tensor. We take the three channels, RGB, and combine all the other dimensions, width and height of the images, into a single dimension. This makes calculating the mean and standard deviation per channel straightforward.
So, how do these means and standard deviations get used in the normalization step?
They're the input to the normalized transform. The transform then applies that specific normalization to new data, bringing it to zero mean and unit variance.
But wait, what about the actual image after the normalization? We see an example of a black image. What's that about?
That's because the normalization scales the data beyond the typical 0-1 range commonly used in image processing. The pixels get rescaled, and the matplotlib image display isn't able to show them. It's not that the data is lost, but it has been altered to a range matplotlib doesn't render properly.
So, we have to adjust the way we display it, right?
Exactly. The image itself hasn't been lost, it's just been rescaled, changing its representation, but it's still there and the model can learn from it.
So, normalization fundamentally improves learning in deep networks by
standardizing data distribution to promote consistent gradient descent.
Okay, Samuel, so Jane needs a way to automatically tell birds from planes. Pretty cool problem.
Yeah, a perfect application for AI. It's a classic image classification task.
Image classification? Explain that.
Basically, training a computer to recognize different things in images. Like, teaching it to see a bird and know it's a bird, not a plane.
So, you're saying it's like teaching a computer to see?
Exactly. We'll show it tons of pictures of birds and planes, and the AI will learn to spot the key differences, like wing shape or size, or even the way the light reflects.
And you're using the Safar 10 dataset? What's that?
It's a big collection of images, a bunch of different things like birds, planes, and more. We'll filter it. It's got tons of pictures. That's the training data.
So, how does this training work? Like, how does the AI learn?
The AI looks for patterns in the images. It analyzes the pixels, identifying features associated with birds. It's like, through trial and error. It compares and adjusts its algorithms based on whether it's correct or not.
That sounds complicated. How about a real-world example?
Imagine teaching a dog to recognize a ball. You show it a ball and say ball, repeat this many times. Eventually, it learns to associate the image with the word.
So, the more data, the better? What if the photos aren't perfect?
Yes, more data is usually better. But there are still potential challenges. It's important the images are high quality and representative. If they're blurry or don't show the features well, it might be tricky for the AI to learn correctly.
Right, that makes sense. So, what happens if the AI gets confused sometimes?
That's a possibility, and it's part of why we have something called validation data. That's a separate set we use to evaluate the AI after it's been trained. We want to see how accurately it generalizes to new images it hasn't seen before.
Interesting. That seems like a good system for Jane. So this AI will automatically filter out the planes, saving her time. Okay, Samuel, so we've got this dataset Safar 10. How do we pare it down?
Right. Safar 10 has lots of stuff. We only want birds and planes. A clever shortcuts to filter it.
Filter it? How does that work?
Instead of making a whole new dataset class, we just pick the images and labels that fit.
So, you're just grabbing parts of it?
Exactly. And we renumber the labels to be in order. Makes it simpler for the model to learn. It's a clever way to work with smaller data, you know?
So, what's the label underscore map doing? Like, what's it mapping?
It's saying, label 0 stays 0, and label 2 becomes 1. Simplifies things.
Okay, but how does that make our model work better?
It simplifies the training. The model learns from a simpler representation.
Why just 0 and 2? Why not say 1 and 3?
Good question. We're choosing the labels that correspond to birds and airplanes in the original dataset, mapping them to a new label sequence.
So, we're effectively making a subset dataset. right?
Precisely. A smaller dataset containing only the things we need.
You mentioned it satisfies the dataset requirements. Can you elaborate on that?
Yeah, it has __len___ and ___ get item ___. Those functions let the training code easily get the size of the dataset and get specific examples.
Crucially, why are we avoiding making a full dataset subclass?
Well, for this specific case, we need only basic functionality like indexing and size. The shortcut's efficient enough here.
So, it's not necessarily better than a proper dataset, but simpler in this scenario?
That's right. Sometimes, simpler is more efficient. It's great for small datasets and when specific methods are enough. But if we run into limits with this approach, a full implementation is an option.
Right. So, we have data. What's next in this deep learning pipeline?
Now, we need a model for that data.
Okay, Samuel, so we're talking about fully connected models. We're flattening images, right? Like squishing them into one long line. How does that work in practice?
Yeah, imagine an image. It's got width, height, and color channels. We're just taking all those pixels, all those numbers, and stringing them together.
So, 32 by 32 by 3 gives us 3072 numbers. Makes sense. But what about the neural network itself?
Exactly. That's the input layer. This new model takes that 3072 number input. Then, there's a linear layer.
A linear layer? What's that do?
It's like a giant multiplication table. It multiplies your input by a bunch of weights and adds some bias. Outputs a new set of numbers.
And then?
Then, we apply an activation function. Like a tan. That's a crucial step. It introduces nonlinearity. Without it, the network's just a linear transformation.
So, what does nonlinearity do?
It lets the network learn much more complex relationships. Linear models can only learn straight lines. But nonlinearity, like tan, allows it to learn curves and complicated shapes. Think of learning to identify cats versus dogs. Tan might pick out subtle differences, like the curve of a tail or the angle of a paw.
In another linear layer?
Yep. That one takes the output of the hidden layer, reduces it to our desired number of classes, like 2 in this example, cat or dog.
So, we're taking 3072 and squishing it, then applying layers and nonlinear transformations to get our classes out?
Exactly. The whole point of hidden layers with nonlinearities is to learn these abstract relationships from your inputs. It learns to compare pixel features in a way that helps distinguish the classes you want.
But 512 hidden features? Why not more or less?
That's a good question. It's often a balance. Too many, and you risk overfitting. The network memorizes the training data, not really learning the underlying patterns. Too few, and it might not learn the necessary complexity. Finding that sweet spot is a common tuning problem in these models.
You mentioned this fully connected model being unaware of spatial arrangement, right?
Yeah. It doesn't know pixels 176 and 208 are near each other. It just treats them as individual numbers. That's a key difference from convolutional neural networks. They do look at the spatial structure of the data. They look at local correlations within the image.
Fascinating. So, this model is a basic approach, but understanding it helps us understand how more complex models build on these fundamental ideas?
Absolutely. It's a great foundation for understanding the power of neural networks.
Okay, Samuel, so we're talking about classifier output. This output is not just a temperature, right?
Exactly, Alfred. It's categorical. Like, is it an airplane or a bird? We need a different approach than just a single number.
So, how do we represent that?
We use one-hot encoding. Imagine a vector. 10 means airplane, 01 means bird.
Okay, makes sense. But what if there are more categories? Like Safar 10 is 10?
We just extend the vector. 10 entries, and we just have 1 to represent the category.
So, the network's goal is to output those one-hot vectors?
Ideally, yes. But in reality, the network might not be perfect. It might output something like 0.8, 0.2 for an airplane.
So, instead of a hard and fast categorization, it gives probabilities.
Exactly. The network is telling us the probability of each category. That's a key concept, right?
Yeah, the 0.8, 0.2 example. What does that mean?
It means there's an 80% chance it's an airplane and a 20% chance it's something else.
So, how do we make sure the output is truly probabilistic?
Well, we need two things. First, every value must be between 0 and 1. Second, the values need to add up to 1. That's where the softmax function comes in.
How does the softmax enforce these rules?
It's a mathematical function that transforms the raw output of the network into probabilities. It does so in a way that guarantees every number is between 0 and 1, and they all add up to 1. It's a really smart way to ensure the output is a proper probability distribution.
So, a tough constraint solved with a cool mathematical trick.
Precisely. Softmax is differentiable, meaning we can use it in our training process without losing the gradient information. This is crucial.
So, it's a smart way to use probabilities in a differentiable way. Thanks for clarifying. All right, Samuel, we're diving into representing outputs as probabilities. So, softmax, what exactly is it doing?
Softmax takes a vector of numbers and transforms it into another vector where all the values are between 0 and 1, adding up to 1. Think of it like assigning probabilities to different outcomes.
Okay, so it's like a weighted average, but ensuring the results are probabilities?
Exactly. It converts raw numbers into probabilities, something crucial for classification tasks.
Cool. And the code? Can you walk us through that?
Well, the core idea is exponentiating each element and then dividing by the sum of those exponentials. It's a neat way to normalize them to probabilities.
So, in simple terms, it's making sure everything adds up to 1?
Precisely. It ensures the output represents a valid probability distribution.
And why is this normalization important?
Without it, you wouldn't have a meaningful probability. Imagine predicting the chances of something happening, but the numbers don't add up to 1. It doesn't make sense.
Got it. And what about the NN? Softmax part?
The NN module in PyTorch provides a way to apply softmax across batches. It lets you specify a dimension for the function to act on. You know, because you might have multiple samples in a batch. It's very convenient.
Makes sense. But is there a practical example where this is used, like something we can visualize?
Absolutely. Imagine training a model to identify objects in images, like cats versus dogs. Softmax would take the output from the model and turn it into probabilities. You could see something like 80% chance of a cat and 20% chance of a dog. That's the power of probabilities.
So, this is really crucial for getting our model to output meaningful results in classification tasks, right?
Exactly. It turns raw scores from the model into a probability distribution, which is how we make decisions. You know, it's a powerful tool.
And what about this grad_fn thing?
That's the gradient function, part of the computation graph. Crucially, it lets us calculate gradients during backpropagation. This is essential for training the model, to update the parameters to get better predictions.
So, this entire process, softmax and gradient calculations, makes the model better at classification?
Absolutely. You can think of softmax as a vital bridge between the raw outputs and the meaningful probabilities. It's how we make sense of predictions.
Okay, Samuel, so we're talking about classifying images, right? We're moving away from MSE. Why?
Yeah, Alfred. MSE, while useful in some situations, isn't ideal for classification. It tries to perfectly match the output to 0 or 1, but we don't need perfect reproduction. We just need the correct class to be the most likely.
So, we're aiming for probabilities, but not necessarily perfect ones. Makes sense. And what's this new loss function?
It's called negative log likelihood, or NLL. It focuses on maximizing the likelihood of the correct class.
Maximizing the likelihood. That sounds important. Can you explain that a little more?
Sure. Imagine we have a picture of a bird. NLL wants the probability of it being a bird to be higher than the probability of it being an airplane. It doesn't need that probability to be exactly 1.
Okay, so it's more about the relative probabilities. Interesting. And what does that figure show?
The graph, figure 7.10, shows how NLL changes with the predicted probability of the target class. If the probability is very low, the NLL shoots up. But when the probability is above 0.5, the NLL drops slowly.
So, a high NLL means a poor prediction. Makes perfect sense. How does this loss function work in practice?
Well, we run the forward pass, get the output from the last layer, apply softmax, and then calculate the probability of the correct class. We take the logarithm, flip the sign, and add it to the overall loss.
Okay, but we're not just taking probabilities, are we? Something else is involved.
Right. PyTorch's NN NLL loss actually takes the log of the probabilities. Using nn.log softmax instead of nn, softmax handles that numerically better, preventing issues with very low probabilities.
Right. That's a good point about numerical stability. Why is that necessary?
Taking the log of a tiny number can lead to computational problems. Log softmax addresses this. It's crucial for getting accurate results.
So, using log softmax as the output layer is key. You've shown the model. How do we apply it?
We modify our model to include nn.log softmax, and we create an nn.nll loss object. Then we pass the output of log softmax and the actual class labels to the loss function.
And we see how the result compares with MSE, right?
Exactly. The graph, figure 7.11, contrasts the two. The cross-entropy loss, using NLL, has a nice slope, even for bad predictions, while MSE flattens out too quickly. That's why it's better for classification.
Makes perfect sense. So, this is the way to train a classifier now? Smooth and efficient.
Correct. This sets us up for training the classifier in the next step, following a familiar training loop approach.
Okay, Samuel, we're diving into training classifiers. So, this chunk talks about stochastic gradient descent. Can you break that down for us?
Sure. We're using smaller subsets of data, not the whole dataset.
Why is that better?
It's more efficient, and it helps avoid getting stuck in local minima.
Can you elaborate on local minima?
Imagine a valley. Gradient descent with the whole dataset might get stuck in a small valley, even if a bigger, better valley exists elsewhere. Using smaller batches, we randomly sample, kinda like taking multiple steps in different directions. This helps us get out of those local valleys.
So mini batches are key for training?
Definitely. The data loader is crucial. It shuffles the data each epoch, making sure the sequence of gradients is representative.
Wait, what's an epoch?
It's one complete pass through the entire training dataset. So, each epoch shuffles the data for the next batch of training.
And the batch size?
We set that to, like 64 images at a time. It affects how often we update the model's parameters.
Interesting. How does this new method change the training loop?
The training loop now has an inner loop, processing samples one at a time within each batch. We calculate the gradient for those samples.
So, instead of accumulating the gradient for every image, it's doing it in batches?
Exactly. We calculate the gradient for a batch, update the model's parameters, and then move on to the next batch.
So, you're saying a lower learning rate is also important, right?
Yes, absolutely. The gradients are estimated on smaller subsets of data, which might be slightly off. Using a lower learning rate makes sure we don't overshoot, making the model more stable.
You mentioned something about overfitting. What's that?
Overfitting means our model learns the training data too well, almost memorizing it. It performs exceptionally well on the training set, but poorly on new, unseen data.
So, how do we measure how well it does on unseen data?
We use a validation set. We test the model's accuracy on this separate set.
That sounds crucial for measuring real-world performance. So, what about model depth?
More layers, like having a deeper model, means more complexity, potentially more accuracy, but also many more parameters.
More parameters mean more calculations. So, is there a trade-off there?
Exactly. Deeper models can perform better, but might be computationally expensive, especially if dealing with large image sizes. We saw that in our example. Adding layers did increase accuracy slightly.
Great insights. Now, you mentioned model parameters and size. How does that impact things?
A lot. More parameters means more calculations and potentially overfitting. With big images, even a fairly simple deep model can have millions of parameters, making it difficult to train. We need substantial computational resources.
That's a big takeaway. How do we know if our model is overfitting?
Compare the accuracy on the training set versus the validation set. If the training accuracy is significantly higher than validation accuracy, then we are probably overfitting.
Great. So, we need to carefully balance complexity and computational costs. Okay, Samuel, so we're talking about fully connected layers. It sounds like they're a bit problematic when it comes to images, right?
Yeah, Alfred. They're conceptually straightforward, but they have a key flaw for image recognition.
What's that?
They treat the whole image as one big vector. So, every pixel connects to every other pixel in the output.
Wait, that's a lot of connections?
It is. Imagine a 32 by 32 image. That's 1024 pixels. Each pixel connects to all 1024 others. That's a massive number of parameters.
So, what's the problem with that massive number of parameters?
The problem is translation invariance. If you shift an object by just one pixel, the relationships change entirely for the network. The network has to relearn everything from scratch.
That's a lot of wasted effort. So, you need a huge amount of data.
Exactly. To account for all the possible translations, you'd need to feed your network way more data with the object in every possible position within the image. That's called data augmentation, and it's costly in terms of storage and processing.
So, the network needs to learn the same object in different locations.
Yes, it's like a detective needing to recognize the same person in multiple photos, even if the person is slightly out of frame. They are all slightly different cases.
That makes sense. So, what's the solution?
Well, convolutional layers are the solution. They cleverly learn the relationships between nearby pixels, and the network doesn't need to be trained for every single position.
Interesting. What's the key difference?
Convolutional layers only look at local regions of the image. They learn features at specific locations, so shifting an image doesn't change what the model has learned. It's more like recognizing patterns, not just specific arrangements of every pixel to every other pixel.
Ah! So, that's the key difference.
Exactly, Alfred. It's like recognizing the shape of a car from multiple angles. A fully connected layer needs to see the car from every angle for learning to be successful, whereas a convolutional layer can learn the pattern, the car directly.
So, we've built a basic classifier. Solid work. But you mentioned a shortcoming. What's this 1D thing?
Yeah, treating 2D images as 1D data. A big simplification. Think of it like trying to understand a painting by only looking at its pixels, one after another. You lose so much crucial information. It's like trying to understand a song by just listening to the individual notes without the melody or harmony.
So, we're missing something fundamental?
Exactly. Images have a spatial relationship, a 2D structure. We're ignoring all that valuable information. It's like building a car without considering its shape and form. You just have a bunch of unrelated parts.
And translation invariance? What's that about?
Translation invariance means the output shouldn't change if you shift the image. A cat is still a cat whether it's in the upper left corner or lower right. Our current model doesn't understand that. It sees the cat differently, even though it's the same object.
You're saying our model is missing a crucial piece of the visual puzzle?
Precisely. It's like reading a book. You wouldn't understand it if you just scanned every word individually. You need to see the sentences, paragraphs, and the overall structure. Images are the same.
So what's the fix? How do we handle this translation issue in future models?
That's where the next chapter comes in. We'll learn how to leverage the image's 2D structure. We'll unlock a whole new level of understanding and accuracy.
Okay, so if our model isn't ideal for images, could we use it elsewhere?
Absolutely. You could probably use it with tabular data and time series data from Chapter 4. It might even work with text data if it's properly represented.
So, it's not useless, just limited?
Exactly. A valuable starting point, but still limited to specific kinds of data. This model has its strengths and weaknesses, you know? Important to understand both.